Hey folks, in this video we are going to be talking about reflection and refraction. So first we need to talk about the ray model of light. We can talk about light as an electromagnetic wave, which is what it is, but sometimes that carries too much information. So when the wave nature of light is unimportant to what we are studying, we will often represent light as rays. This will allow us to look at the important features without getting bogged down by the details. And we can always translate back to the wave picture when needed. The light ray is going to point in the direction that our wave is propagating. So here is the idea. On the left, we have these lines represent the crests of an incoming wave. And the blue arrow is the direction of propagation of that wave. And for reasons we'll talk about shortly, the light changes direction at this boundary. And we can see that we have waves here that are getting more bunched up and it's moving in a different direction. So when we're just dealing with rays, we can drop the wavelengths and the wave crests that are there. And we can drop the wave fronts. I do feel that it's helpful to show the difference between these two using a PhET simulation. Here we have that PhET simulation, and I'm going to switch over to the wave model now. This is a laser that we have here, and the laser is sending light out into the world, and we can see that light wave move. We can see it moving forward. The red in this picture represents the crest of a wave, and the black lines represent the trough of the wave as it moves forward. So this is what the electromagnetic wave from a laser is actually doing, what it actually looks like. We have these waves that are coming in, crest, trough, crest, trough, crest, trough, that alternates. For a lot of what we're going to study, this is too much detail, and we can much more easily draw just light rays, which are just the beam without showing the wave features. And so that's what we're going to do for the time being. We're going to draw just the ray part of the light wave, keeping in mind that there actually is an alternating series of crests and troughs of waves as it moves forward. Let's talk more about what's going on here. I've got some annotations in the PowerPoint to help us out. Let's see, moving forward. All right, so light does two things. This is experimental observation. You grabbed yourself a piece of quartz or glass or whatever, plastic, you could observe both of these. Well, you need a mirror for the first one, right? Light does reflect. That's number one. It bounces off of things like mirrors. The other thing that light does, which you may or may not be familiar with, is that light refracts. That's what's on the right there, refraction. And light changes the direction that it's propagating when it enters a medium. This is another observed behavior of light. So the light here is coming in from the bottom left. It changes direction when it's inside of this cube, which looks like it's made of some sort of plastic, and then it returns back to its original direction of propagation when it comes out the other end. So that's observational behavior of light. Let's talk more about what we observe when we see this. So we've got the light rays drawn in from that laser diagram. I drew in some arrows as well. The light ray is moving down and to the right, and then it does both at this boundary. It both reflects and refracts. The light that bounces off reflects. The light that passes through, it bends, it changes direction. So let's talk about it. We've got a laser up there, and the laser is being turned on in air. The index of refraction of air is 1.0023 significant figures. It enters a glass boundary. That's what the purple zone is. It has a higher index of refraction of 1.50, so a higher optical density. The light slows down in the glass. We call the light over here incident light. It's incoming to this boundary point. We call this angle the angle of incidence, theta subscript INC for angle of incidence. We call this light that bounces off the surface the reflected light. Makes some sense, it's the light that reflects. And we call this bouncing angle the angle of reflection, theta subscript REFL. And then this is our transmitted light. It transmits through into the glass. It passes through. In other words, light gets refracted, and not in other words, but that transmitted light does get refracted. That's what happens. And we call this 30.7 degree angle the angle of refraction. So we have an incidence angle, which in this example is 50 degrees. We have a reflection angle, which in this example is also 50 degrees. And we have a refraction angle, which in this example is 30.7 degrees. This dashed line we call a normal or a perpendicular line, and it is the reference line from which we will measure all of our angles. The law of reflection. We can see in this example, and it is always true, that the angle of incidence is equal to the angle of reflection. Always true. If you've got a pool table at home, you can check this out. Grab yourself a billiard ball, bounce it against the wall of the pool table, and you'll see that the incoming angle and the bouncing off reflecting angle are the same. That's what I just said. When light is incident on a boundary, it is always true, or sorry, this isn't what I just said, but it's worth saying. When light is incident on a boundary, it is always true that some light reflects and some light transmits. Some of both always happens. A mirror is an object where most of the light reflects. That's what we call mirrors. It's when we get a more reflection than refraction. Usually these mirrors are silvered, and that's what gives it its reflective properties. Glass is a material where most of the light gets transmitted. Not all of it, right? All of us have looked into a window and seen a reflection also, right? We've seen some light reflect back. It's a very translucent reflection compared to what you see in a mirror because not nearly as much of the light bounces off of it. Most of the light transmits through. And when light transmits into a new medium, it also changes direction in the new medium. That's that angle of refraction being 30.7 degrees, not 50 degrees like the incidence angle and the reflection angle. And this vocabulary word here, refraction, is that process. Refraction is the changing of direction of light when it enters a new medium. Refraction is the changing of the direction of light when it enters a new medium. So here we go. We're going to talk about Snell's Law next, which relates the angle of incidence and the angle of refraction. You'll notice that we relabeled the angle of incidence with theta 1 now instead of theta INC. And we relabeled the angle of refraction theta 2 instead of theta REFR. And this is convention for Snell's Law. So Snell's Law is our way to relate the angle of incidence to the angle of refraction. And this is the observation. The value n sine theta, so you take your index of refraction, you multiply it by the sine of the angle, is constant for light incident upon a given interface between two materials. So if we take this 50 degree angle, take the sine of that 50 degree angle, multiply by 1, and if we take the sine of this 30.7 degree angle, multiply by 1.5, we should get the same thing. Snell's law is more commonly written this way, where n1 sine theta 1 is equal to n2 sine theta 2, where the n's there are the indices of refraction of our two mediums, and the thetas are the incidence and refraction angle respectively, measured relative to the normal. So in this example, I mentioned this earlier, but if we take n1 sine theta 1, that's 1 times the sine of 50 degrees, punch that into a calculator, you get the number 0.766. n2 sine theta 2 for us, that's 1.5 multiplied by the sine of 30.7 degrees. Punch that into a calculator, you get the same 0.766. They are the same. So for our glass-air interface, the constant value that n sine theta has is 0.766. And then our last message here is a warning. You must measure angles relative to the normal line when using Snell's law. It is tempting for students to use the angle with the boundary, which would be incorrect. We actually use the angle with the normal. Sometimes the normal line is drawn to remind you, sometimes it's not. Sometimes you got to remember to do that on your own. So Last slide here are just some consequences of refraction. What does this look like to us when light is entering our eyes? The left is an actual photograph, no Photoshop, no photo manipulation. Grab yourself a glass of water and a pencil at home, drop it in there, you'll see this same thing. You'll see that the light changes direction inside of the water because it moves slower. And with that direction change, it looks like it's at a different angle in the water compared to when it's not in the water. So check this out, try it at home. If you are ever going spearfishing, which I doubt many of you do, but it's kind of cool, one thing you need to look out for is this refraction effect. So if you have a fish down here, the light entering your eyes is going to refract when it gets back into the air. And then our brains aren't able to determine that there was a bend in that light. And so where your eye thinks the fish is in this straight line path down here. So where your eyes see the fish is higher than the fish's actual position because of refraction. So if you're going spearfishing, you should actually aim lower than the fish's position that your eye sees, because the fish's actual position is lower than what your eyes are seeing. So these are just some consequences of refraction. In our next video, we are going to try and understand the concept of refraction from a more conceptual point of view.